So now we'll move on to the idea of independent events. And if events are independent, the probability of an event is not changed by the outcome of the other. So examples of this are like dice rolls. Just because you roll a 6 the first time doesn't mean that there is lower chance of a 6 on the second roll. It's independent. And there is a rule for this. And when we do conditional probability, we'll see a bit of a proof of the rule. But the rule is P of A times P of B equals P of A intersect B. So I can show this in a bit of a tree diagram. Like, if we could say like heads and tails. And maybe the probabilities for heads and tails are not equal, but they didn't change no matter whether a head or tail was flipped first. That's the important part. We multiply the probabilities along, so that should make sense. Whereas, say, something a bit more conditional, maybe. I walk to school versus I drive to school. Late, not late. Late, not late. Maybe this might not be independent, because say if there's a probability that I walk to school, then probability that I drive to school like that. But perhaps if I walk to school, I'm more likely to be late. So now the probability of being late or not late changes based on what has happened here. And then obviously if you, as you know, on a tree, you multiply the branches across, and that's why for independent events that multiplication rule will work. But because we've got not independent events, if you went and calculated the probability of being late, you'd have to do 0.6 times 0.8, and then add that to 0.4 times 0.4 to get the total probability of being not late. And as that would be very obvious, then it'd be crazy to say, okay, well then you go 0.6 times whatever that is to get the probability of being of being not late when you walk to school. Because you're factoring in part of the probability that involves driving to school. So that's why it will not obey that rule of PA times PB equals PA intersect B. And most events are not independent, and you may be asked to show if things are independent or not. And so basically you would compute PA times PB and see if it equals PA intersect B. And if it doesn't, they're not independent. But if they are equal, then it is independent. So I'll just go over and also if you know that they're independent, you could do things like PA will equal PA intersect B over PB and stuff like that. I'll just go over like how we look at tree diagrams here. So here what I've done, this is a good example. We start from the start, then we do all the possibilities. So I've written out walk to school and drive to school. And on the branch, before the event, I write the probability of the event. And then, after that, we assume we're walking to school, that's already happened. Now, given that, what's the probability of being late and not late? And then what we can do is add the probability at the end of the branch. Like that. And then we can use, this is a helpful way of figuring out some probabilities. Obviously there are a lot of different questions. Do a lot of practice and watch the videos on the practice video, on the practice questions as well.